you, the students who attended the previous session. I will recap a bit from the beginning, so hopefully on Friday you are able to remember some of the things we already discussed. And one of the first things to start discussing is the scale. So casting occurs on different scales, and that's why it's so challenging, because we have things happening at machine size dimension, and you will see that today in person. And for those who are familiar with continuous casting, the order of size of the machines in meters, of course. And this translates to incredibly challenging process where you have to deal with the industrial scale of the machine, what is happening in the mold, for example, which is in the order of meters, and then go all the way to the micro dimension, where we have, for example, slag infiltration and shell growth happening in the order of millimeters. And we discuss about the slag infiltration, how it controls the process. And this happens in a very thin layer of less than 1 millimeter or 1 or 2 millimeters. So coexisting of these scales makes it very challenging process. And then at the end, at the smaller end of this, we have the microstructure formation, and that occurs even smaller scale. So the challenge for casting is to cover all this range from micro, and I would say also nano, including what's happening at atom levels when we are talking diffusion and segregation, all the way to the casting size and the products, which are the thing which is relevant for us. Now, if we look at it from the other side, so we ended up we started from the machine, went to the microstructure. So if we look at it from the other side and start from the atomic scale, so we can see that phenomena such as nucleation occurs in the nanoscale range. So you see 10 to the minus 9. And all the structures that we will discuss today, and we will see, they are happening very often in the micro scale, so hundreds of microns for a dendrite, or even bigger. And the grains also, although here we have them defined as 10 to the minus 3, we can have single crystal blades. I think we were discussing that in the previous session. That could be the whole size of the component could be a single crystal. So grains can go from a very wide range of sizes, from very small in the order of millimeters to actually complete components in crystal size. And again, what happens in the different scales, the physics that we encounter, is what makes solidification very challenging. However, what is driving solidification, and we discussed also in our session in Spain, what drives casting and what is casting. From the very beginning of our first session here with the students, we made a definition, which is extracting heat from a melt to produce a solid shape. And therefore, the driving force for producing the solid is the extraction of heat, and this, as a function of time, produces a cooling rate or a cooling time, right? And this is going to be fundamental for the casting process. How this cooling occurs is what determines the types of structures that we will encounter during solidification. And some definitions which are interesting to have, and we need to have, is, for example, the velocity of the solidification front. In our previous session, you remember we were discussing the liquid. We were discussing that there is an isotherm, which is our T liquidus. We also have the T solidus over here in the bottom, and everything in between is going to be our Moschi zone. And keep in mind, and we discussed this in the previous session as well, how the thermal gradient, the solidification front, will grow opposite to the extraction of heat. And the speed at which we extract this will determine how fast this solidification front or this isotherm advances. So this is going to be very important because it's going to define basically our solidification front speed. Another interesting definition here will be then we have the dendrites growing, and we have the interdendritic liquid, which is everything that is in between the dendrites, which is yet to be solidified. And I actually would like to thank here if Alex, and I'm borrowing many of these figures, which I consider they are fantastic. So I'm always trying to have the reference here. And if during the course you are interested, I think we will share these slides eventually, Salish and Nora, or at least if you are interested, probably we can put a list of references for everyone, so you can follow all the figures and many of these interesting papers which we have used for collecting the presentation. The same goes for the classic work from Fundamentals of Solidification from Kurtz. So what happens when we complete the solidification? Well, we end up with a macro structure. So the microstructure gives rise to a full structure. And this could be, like in the example on the left, an ingot. And when we cut it and analyze it through etching, we can reveal the structure and we can reveal the grains that occur. And it tells us a bit about the story of how the solidification occurred. Another couple of definitions here which are interesting for you to have is most, of course, of the times when we start the solidification, it occurs from the walls. They act as the starting point for solidification because it's obviously our coldest point in the strand, in the ingot, and the growth occurs towards the center of the ingot in this case, and this growth in form of clear columns, therefore the reason called columnar zone. And once we achieve there's a certain length of solidification, there is often a transition, although it may be possible that we just have columnar grains all the way. Very often there's a transition where we start nucleating in the center, and this creates an equiax zone where we have dendrites growing in the center of the ingot. We will also go through what's the transition zone, which is called the columnar to equiax transition. But let's start with the classic, the nucleation. And very, very interesting and important for you to know, for pure metals, we will still have dendritic formation. We will still have grains. What is not going to be possible when you do a macro etching is to see differences in the composition within the grains. They will be formed, of course, of a single phase, and you won't be able to see any differences. Whereas, as we had in the previous session with the phase diagrams and the description of the phases that we encounter, especially in steel, when we have an alloy, we have alloying elements, not a pure metal. After we have nucleation and we have the growth of the grains, and we have the final solidification, when we do an etching and observation under the microscope, we will be able to see differences. And this difference will be the different solidification of structures that happen as we went through the phase diagram that you remember in our previous sessions. So those are the two differences. You will see clearly, and here in the picture on the bottom is very clear how it is represented. So you have pure alloy, you have grains in the but consistent of one single alloy in the pure metal, sorry, and in the alloy you will get grains where you can see clearly phases inside. Okay. But what drives solidification is basically energy. Again, we come back to the concept. What are we doing to produce solidification? We are extracting heat. So the change in energy in the system is what drives this. So in this case, atoms in the melt vibrate and collide randomly. And this is the source of energy in the system, of course. So what we need to do is to decrease this energy. We need to cool down to a point where we start forming nuclei. And this might be 100 degrees below the freezing point, since nucleation requires an amount of energy for reaching a critical radius. So what will happen when you are just in this area? Let me see if I can bring my pointer. In this area, is you need to drive the nuclei formation to a lower temperature, because if you are in this limit, it's very easy for the nuclei to appear, disappear. So you need to extract heat further. Basically, that's the explanation here. If the nucleus does not reach this critical size, it will eventually dissolve before the growth starts. So it is possible to decrease the temperature of a melt below the solidus temperature without solidifying, and this is referred to as undercooling, right? In contrast, for solid metals, the atoms are packed closely and well-defined into crystallographic structures that require least energy. So is the least energy form of the system. And how this packing occurs is what will define the phases. So if we have a body center or a phase center structure, it will be how this packing is done, and how the other atoms for the alloying element fit into this structure will also affect what kind of structures we will get, microstructures we get at the end. I find this visualization amazing. This is the, I hope, yeah. So this is the first ever atomic resolution video of salt crystals forming in real time. So here you have an image. It is by a group of researchers in Japan. And what you can see here is that the atomic resolution video of a carbon nanotube confinement. So you can see here the edge of the carbon nanotube. And we have the salt crystals form basically randomly here. And then you have the formation of the structure. I hope you're also able to see this online. And you're able to see it here clearly.
Yeah, it's visible. Good to see.
Excellent. So you can see clearly here how some of the atoms order to form crystals, and they are later move out into the experiment. So to me, it is fantastic to be able to actually see the ordering of atoms to form to an actual crystal, and how this happens in real time. So it's no simulation, this is an experiment. And here you can see clearly, I hope also, when nucleation events happen, you can see where we start having some structure and where we have a phase transition as well. And finally, we continue the growth. By the way, if there is any question here or online, we can always try to address it as it goes. But we will also have a final Q&A session if it's needed. Of course, nucleation is affected by solid elements. The grain size and microstructure are not only influenced by the addition of particles, but also the specific solid element additions. So here you have some examples where you have complete different, because of the way these alloying elements interact with the structure, we will produce different, especially grain refinement for those who are interested in the industry to have finer structures, which very often will produce better performance. So we use this nucleation. We can have inoculants to favor a larger number of nuclei, so we get a finer microstructure, but we can also have the addition of alloying elements which fix microstructures as they are being solidified. So that's a very interesting application on how to use alloying elements. But at the end of the day, what we are looking for is to fix certain types of structures, as I mentioned now. And this will be a strong function of course, the composition of our alloy, the elements that we have, but also the cooling rate, as we were talking. And again, this figure from Kurz is fascinating, because I think shows very clearly how there's limits on how we get, for example, go from a planar front when we have extremely fast solidification to the formation of columnar dendrites. And there is a limit here where we have the transition to equiax dendrites. And basically casting occurs in this range of solidification front speeds. and energy and cooling rate for the system. So basically, what we are trying to do very often in our research is try to map what kind of structures we will form. I hope you remember also the session in thermocalc that we had with Ting. And in this session of thermocalc, what we studied was the kind of phases that we will encounter. In this kind of map, what you are able to do is not only what kind of phases, but what are the specific grain sizes, what are the specific, well, we will talk about primary and secondary arm space and so on later on, but what are the specifics about the microstructure that are influenced by the kinetics, basically the time that we are taking for cooling down. So if we go to the solid liquid interface morphology and temperature, we see that in a pure metal and at the mold wall, like we saw in the ingot example, columnar grains generate a planar interface, which advances opposite to the heat flow. Whereas in the case of in the open melt, let's say, the dendroids grow radially in the same direction as the heat flow. So we have this case, for example. And in the case of alloys, again, the morphology at the mold wall is usually dendritic. So we start with a columnar growth, and also the quiax growth is similar. Here a note, in columnar growth, the hottest part is the melt, while in the equiax, the crystals are the hottest. So the melt must be always cooled below the melting point. So we always need to have an undercooled melt before equiax crystals can grow. I hope we are able to have the audio of this. So how do we do to put the audio of this video? So I think the explanation is really interesting. So I'll try to run it.
And there should be an audio from the video now. I don't want to do something and then it messes up the entire presentation.
No, I get it. Because we just need to activate the audio of this, right? As if I
No, that's going to activate the speaker.
Yeah, but not mine. Let's see.
But you also have the mic on, so it's going to.
Well, I think if you can share, but not your screen, but the PowerPoint, and then you can choose share with sound. Your Teams, you're now sharing your screen. But in Teams, you can select sharing the PowerPoint presentation instead of the screen.
Okay, so let me see.
Then you can choose that you want to share it with sound.
Share screen, or what did you say, Stefan?
No, share.
No, not the screen, but the
presentation.
You can select the PowerPoint itself.
So
if you go on Windows, not on screen.
PowerPoint live.
Oh, good.
Then let's see if.
Yeah, here it's blue.
Yeah, there it is.
Can you hear the description from the video?
Yes, we can.
Great.
Yes. Okay.
Limitations. The only numerical parameters are the surface energy function and the dimensionless undercooling. With isotropic surface energy, tip splitting is the characteristic behavior. No direction is preferred. More and more fingers are produced as the seed grows. With fourfold anisotropic surface energy,
Silas, you have to unmute.
Yes.
Oh,
Pavel,
yeah.
wait a second.
Yeah.
Yes. Is it okay now?
Yeah.
Great. So it is a bit of an old school video, but it gives you a feeling of how the solidification structures start depending on anisotropy, but also the rate at which it grows. So I think it gives a really clear representation of how this map on the right occurs. It's a bit weird, my. So if we continue now to look at dendritic growth, you able to see my screen again? Yeah. This is also a fascinating video. Where we can see the actual growth of the dendrites. So in this case, what type of growth do you think would be? This is columnar growth, which is happening from one side. So for our students here in the room, where do you think is the heat flow direction? Opposite. So it's going from right to left. And if we play the video again, then we can see clearly how the dendrites grow. And we have the definition of a few points here. First, the primary arms, which are these axes where the dendrites are going. And then we have also the formation of branches. And these branches are the secondary arms. Okay, these branches themselves that have arms too, which are the tertiary arms and so on. And what is important is that we use these characteristics for the dendrites, primary arms, spacing, which is the spacing between the axes, and the spacing between the arms, the secondary arms, to characterize the solidification structures. So that's what this slide is about. But also it's fascinating to see this experiment, how we have growth and how we have also nucleation here, and you can see it on the left side. Let me return this video. Whoopa. So you can see here, for example, how we have one of the arms becomes the root for a new primary arm. So it's also for you to give you an understanding. It's not that just one primary arm continues until it stops. The primary arms could become, the secondary arms could become primary arms and vice versa. So there could be switching between all of them. And this video is fantastic to explain that, because you can see how very often, for example, here there is competition. One of the dendrites is blocked. So we have the other ones continuing, and we have them growing against each other as well. And for example, now we have the one on the bottom, 1, 2, 3, 4. The fourth is also
Point on the
blocked.
screen, Paul.
Up. The one from the fourth is also being blocked, and this creates the actual formation of grain boundaries. So in the case of grains, unfavorably oriented grains are eliminated as they grow. So you saw in our example clearly how we have a whole bunch of dendrites growing in one direction, and when they are blocked, they form a boundary. And this is what we later on identify as grain boundaries as well. So the grain starts as cells and they become crystals. Another fascinating point here is to look at the columnar to equiax structure. So it's nice we have it on Friday, no exercises, a lot of movies on Fridays. So bear with me. So in this case, we have a aluminum copper alloy, and we see from the beginning, let me stop it there. So you see from the very beginning, we have this cells formation and we have nucleation of the columnar grains, which eventually become very, so some of them die, and then we start also having the formation of dendrites in the free melt here. Nucleation and formation of dendrites. But I'll keep quiet for a moment and let you observe this. So there's a whole bunch of interesting phenomena apart from the transition, where we have the base going from the columnar to equiax. So that transition where you see the columnar sections, one dendrite on the right actually continue growing as columnar dendrite, but the rest we have the formation of these equiaxed grains. And what is fascinating as well is the competition process. Oh, I'll try again. So how they interact, how they stop each other growing, how they actually, some of the arms, I hope you're able to see it here in the online as well. You are able to see how some of the actual grains, the tips of the dendrites, because of convection of flow in between the dendrites, are broken off, and they are also floating up, and they become new nuclei for new dendrites. So yeah, like that. Let me see if we can capture one of those. Yeah, that one right in the center you saw. I will play it back again. So please pay attention to this area. Whoopa. And I'm going to return just a bit more. And then you can see in the center how one of those arms gets expelled, and it then acts as an initiation site for the next, as nuclei for the next dendrite. So fascinating video on understanding how solidification occurs. Well, this also goes into what we discussed. I think we already had our phase diagram session, and we understand what that it becomes a function of what phases we're encountering during solidification. I guess to finalize this part of the introduction of how solidification occurs, I would let you here enjoy a couple of videos. They are actually found in Harry Badishi's site in his Cambridge website. So here is the link in the bottom. And these are the actual transformations where you can see, well, I'll show it to you. Solid state transformation, we have the grain boundaries, and then we have how very fast we have the formation of martensite within the grain. This is not simulation, this is an actual visualization of the solid state transformation. I'll do the same on the right side. So you can see the temperature dropping. And look at the time is of course reduced it's slow down time. And then you can see the formation of lamellar structures within the solidified structure, which is according to what we discussed in our phase diagram session, different types of structures being formed. Good, so this serves as a base introduction to what are the phenomena driving solidification. And if we move into segregation, I will use again this very nice diagram by Alex and add on what is happening at the crystal melt interface. So if we look at the dendrite tips as they are being formed, what we will, if we had the chance to have a fantastic magnifier and track the solidification front at atomic level, what we will see here is that on the right side, so I won't use my hand, on the right side, there's a representation of what we would see. We would see randomly placed atoms of the liquid, and then we will have an interface where we will have the solidified front, not fully, but we will have here at the very much tip, we will have the crystal structure. And in this crystal structure, as we were discussing, depending on what alloying elements, the size of the atoms, and how they fit into the structure, some of them will be accepted in in a more efficient way, and some others will be rejected. And you remember in our previous session, we discussed that this is what we call segregation. Yeah. Some key temperatures that we need to keep in mind as we progress during the solidification is that the temperature at the tip will be our liquidus temperature. And then as we progress on the solidification, increasing the solid fraction. So when we progress in the solid, then we will have the zero strength temperature we already discussed last time. And for those who are joining online, zero strength temperature in this process where we have our dendrites being formed, and now I have some videos to explain, which for example could be very interesting here. So you can see that in between the dendrites there is interdendritic liquid. So at this point, if we imagine, let's imagine that we are able to put a string on this dendrite and a string in this other dendrite, right? And we pull one upwards and the other downwards. When they are not physically fused, when these arms are not fused, which is basically now, and this figure represents really well what we are seeing in the other figure, we won't have strength because there's nothing fusing them, right? There will be a point where these two meet, and hopefully we get it somewhere here. We are tracking the front, but you will see here in the back a point where these secondary arms fuse. They get locked. This point, then, if we imagine our example again of being able to pull, will be the first point where we can feel some resistance to the pulling, right? And this point we call the zero strength temperature. How do I move through this? I guess like that. Yeah. The zero strength temperature. Below that, so here you have here the red line representing strength. And below that isotherm, what we will observe is that there will still be some remaining interdendritic liquid, because despite some of the arms have been able to fuse, you can still have flow around them, right? There will be a point where this flow is impeded. It's not possible to have this flow. The structure is impeding the flow go freely. And this is the liquid impenetrable temperature, or LIT. And this region between the liquid impenetrable temperature and the point where we start having ductility on the material, which occurs at lower temperature, is the area for most risk of crack formation, hot crack formation, right? So we actually had that discussion a bit before in the session. You remember that we discussed, well, what would have more risk of forming cracks? An alloy with a shorted solidification range or a long solidification range? And you remember the conclusion of that, the longer one, exactly. So in this case, by the way, solidification range is the distance in degrees from where we have the liquidus to the solidus line, which should be over there on the left. And depending on the amount of alloying elements, very often we will increase this solidification range, and therefore we will have more risk to have events of cracking or hot cracking when we are solidifying the material. Now, in the more specific, if we want to follow a segregation line, and Seppo, here I borrow your excellent lectures. So
yeah, great. You're welcome.
your follow, for example, here the liquid concentration. We know that we follow the liquidus line. We had an entire diagram, a phase diagram session last time. In the phase diagram, and the solid concentration follows the solid line. So at liquidus temperature, the melt composition is the nominal composition, but the composition of the final melt is high. And at the liquidus, the solid dendrite tip has a lower concentration, but it is increasing when the solidification continues. And this is what we call microsegregation. Now we will introduce the other concept, which is diffusion. And you remember we also discussed diffusion, how easy it is for the atoms to move within the structure. And the concentration at solidus, when all the melt has been solidified, is homogeneous again, and the composition is equal to the nominal composition. That's the case of infinite diffusion. But in reality, we discussed that this is not the case, and some small composition gradients typically exist after solidification. If this microsegregation is very serious, we can have the formation of voids, we can have the formation of cracks. You remember we also look at the example of freckle formation in superalloys, and we will come to that example again. So this leads us to back diffusion. So back diffusion is the process of solid atoms diffusing back into the solid from the liquid during solidification. And this happens as the solid-liquid interface moves, and it works to homogenize the compositional difference within the solid material. This back diffusion reduces microsegregations and leads to a fine solidified structure that is closer to equilibrium compared to models that neglect solid-state diffusion, like the classic child model. And that leads us again to our example you remember we discussed during our phase diagram session, and we think in thermocalc that lever rule and child are the two limiting cases, where lever rule represents the complete mixing of the solid and liquid solid is assumed. So we have an equilibrium solidification model, and this is going to be relevant also for our audience in the afternoon, because these will be limiting cases when we model the solidification in terms of numerical modeling. The child model then will be complete mixing of the solid and liquid, and no mixing of solid in solid is assumed. So we have the two limiting cases. Further one, I wanted to also kind of brag a bit about my colleagues, Johan Lang and Peter. I sat down with Lang and I did my PhD with Peter. And it was fascinating to look at the predictions of dendritic solidification. And in this case, one parameter that I wanted to show you here in this picture is how important is to have convection. Again, we were talking about phase transport phenomena in our previous session. So how important is natural and forced convection in this? So you can have gradients of interdendritic liquid, which is driven by the flow between the dendrites and by the differences in density and in temperature in the liquid. And this also enhances segregation effects. And that takes us to this fascinating video by the group of Natalia Shevchenko in, the work by Natalia in HZDR in Dresden-Rossendorf, where we can see, if I can click it, yeah. It's fascinating because you can see here the formation of columnar grains, and we have a map here of the composition of gallium-indium alloys. So we can see the depletion, the depletion of one of the elements marked in blue, and then the enrichment of this element or of this solute in the liquid, the remaining interdendritic liquid as red. And clearly we can see here how it is rejected. Let me play it again. Oh, funny, it's being showed in online, but not in the screen. Now, I can see it in my screen. It's not showing.
Go back and.
Yeah.
No. Now it's.
Yeah, I'll go back in there.
No.
Now it's running. Oh, fantastic. So you can see here, again, some of the events that we were discussing, primary arm for growth. We can see the secondary arms growing. But what is interesting to see in this video, and I have one. I think I have it here in the front longer. Let me see. Yeah, I have it here, another one in more detail, so we can see it. First, you have convective currents. We have the initial. I'll stop it first. Let's see if I can stop it. So you see already outside from the video plane, we have some initial growth. We have some solute rejection into the melt, and this creates already convective currents, which is these red plumes of solid that you can identify, enriched solid in the liquid. And as we progress in the solidification, unfortunately, it's again slowed down in our screen. We have the formation of the primary arms, and these primary arms, of course, compete and collide with each other. But also, you see here this formation of islands where since we are restricting the flow towards the free flow region, then we have how the concentration of the solute is being increased more and more in these remaining islands of liquid. Let's play the video again. As we keep progressing, even at some point, some of these islands, I think we have it in the previous video even better shown, can cause local remelting because of the change this is at the end. You will see it here. I will stop it here for the online. Yes. So eventually we will have the formation of actual channels where we have this enriched solute that is escaping from the structure and forming what I remember my friend publication, he called them chimneys. Like a very appropriate term for Christmas time is coming and for the cold here. And this actually leads to defects called freckles in the ring casting, and they are typical of nickel-based superalloys in the aerospace industry. At the end, and here again I borrow from a very interesting publication from some colleagues in China. I hope you're able to see my pointer. Yes. So this leads you at the end with extreme gradients of composition throughout the component or the ingot. In this case, we are mapping carbon, and you can see that carbon at the beginning is rejected. So we have a depletion in the bottom of the ingot of this carbon, and it's always expelled towards the last remaining liquid, as you saw in the previous video. And as we are progressing with solidification, you can also make a mind picture of this process. If we, maybe I'll try something, maybe no, I cannot do it online now. I can take the presentation online, but we have over here. Where is my ingot? Here. So if at the same time you are able to take in your mind a picture of the structure that is below, giving these segregation maps, you can see we have the columnar grains, we have the equiax grains, and we can see clearly this. Let's imagine that what is happening is exactly what we see in the right picture. So we have the initial columnar growth, and if we look at the segregation map, let's move here, back. Opa. So you can see clearly those green areas that we see in the mold walls will be our columnar grains. And then we will have in the center the formation of equiax. I should use this. The center, the formation of early equiax grains. And then the last remaining liquid will have the highest concentration of carbon, which will also have very likely equiax grains, but are of a very different nature to the grains that we have in the bottom. so very important for you to consider that when you have a casting, there will be compositional variations. It doesn't matter if you did some sampling, or even if you do sampling. Let's imagine you are able to do sampling on this ingot as you are proceeding in solidification, and then you think, okay, my composition is within range, right? But what do you mean? Because the composition won't be homogeneous on the whole ingot. And this happens even at smaller scale. Here we have experience at Sverim casting smaller ingots of 60, 50 kilograms, and you have very significant compositional variations during solidification. So very often it's hard to have an ingot which you can say, yeah, I trust this is the final composition. So it's more of a range depending on where you sample. And that actually takes us where I have a bit of a summary here for solidification, the columnar to equiax transition. Well, the convection favors the formation of equiax grains. The growth factor promotes the formation of equiax grains. Increasing cooling rate reduce the size of equiax grains. So we always are trying to promote the increase of cooling rate because we will have then smaller equiax, which will be better for the performance of the alloy. Small grains tend to be globulitic, large ones to be dendritic, and then we have seen already the competition of the dendrites. In terms of columnar, the grain motions affect the shape of the mushy zone. So we observe now how the columnar grains grow. And the evolution of grain texture and transfer grain size and columnar size can only be predicted with the help of advanced models, which are CAFE and phase field, which unfortunately here our students will not go into solidification model, but for those joining online, we will see that in this afternoon. Then I would take the last, I think we have some 11 minutes more, something like that, to go through some very good example of experimental work we do here at Sverim. And I will take ingot casting as an example. It's fascinating. This is a video courtesy of Udahome, where we are pouring some slag. So the idea is just to let you understand that ingot casting is alive and well. We have our colleagues here in Sverim. We do a lot of research, especially Matthias. I think I saw him joining, and also Niels. They work a lot with ingot casting. So it's alive and well. And I shared this video to show you a bit of what happens. For example, this is at the end of the casting, where we are just emptying the slag from the ladle into basically a container just to be processed afterwards. But you can imagine now that in the real when we are casting components, in this case, the mold is much taller, and then we have a protection surrounding the stream in order to avoid oxidation. But I found that fascinating because you can see the stream of liquid slag going out. So I like it. So in a much smaller scale, we have done our very own pilot trials for casting some ingots. And this is a very interesting case where we started by casting a low melting point alloy. We work here with bismuth tin to model the behavior of liquid steel in continuous casting. We have a continuous casting simulator, which you had the opportunity to see and cast a nozzle during one of our sessions. So we actually use this alloy to make a model casting and do a proof of concept for an ingot and tracking the temperature. And we did a pilot trial. So here I will show you. We are actually borrowing some of the liquid melt from the casting simulator to put literally on ladles or on pots because we are going to cast this. So here you can see our student Daniel Hetman. This was I would say what 5-6 years ago. 3. Sorry, no. It should be 5. 2020, I think, is his thesis. Before, really. So we have here the process Daniel is extracting the liquid. Salish and me are there taking obviously Daniel won't be able to do the pouring. So we are just checking we have enough temperature to do the pouring. One of the characteristics of these alloys is that very oxidizing. So you can see right away, as soon as you take out the liquid, how it forms an oxide layer on the surface. This is very common, especially with things like aluminum, magnesium. They oxidize super fast. So once we had the liquid thing, we should be able to see Salish and me moving this towards the ingot casting area. And it's rather heavy. It is the same density as a steel. So, and here we have our own homemade tundish. And you see, we are doing the ladle to the tundish process.
You almost said that don't try it at home.
Yeah, please don't try this at home.
It's to be done at home.
Yeah, well, so it was a proof of concept to see that, first of all, you could pour in a controlled way by using this tundish. I think this is the second batch, so we were able to have a full ingot, and I will talk a bit about the ingot in a moment. And then now you see here how it's overflown, so we know that we have enough in the ingot being cast. And I hope you are able to see as well here. I think I will move it a bit and pause it. You may think this Esperian people are crazy. Why are they doing this with a low melting point alloy? Well, the purpose was to actually test this mold. So you see here a jacket made of steel, and then you saw some sand. So now our students are experiencing sand casting. So we use sand, but here the interesting bit is that we use another mold to replicate the solidification during continuous casting. So what did we do? We did that casting, and then we what is it not showing the pictures? Are you able to see the pictures online? It's in there.
No pictures in this slide.
Maybe you can.
Yeah, then I'll leave the presentation mode because we missed the pictures here.
Stop sharing and share this window.
How do I stop sharing? Here I'm sharing here.
I'll just do share and then share window.
Yeah, the lecture. Yeah, there. Yeah, now we switch the sharing presentation. Thank you, Sinesh. Now you should be able to see the figures. Yeah, because it's because you need to cycle between them. So what is interesting is we had here a mold. I'm here portraying on the left. So we have a mold, which is a metal mold. So in this case was steel, which is acting as the first nucleation site for our grain. So it's like the first skin which we will use to grow the structure. Then we have sand, which acts as a barrier for, it gives us a very good insulating properties. And this allows us to have a softer cooling rate. The more sand we have, we reach a lower cooling rate. And this is to be able to replicate the type of cooling rate we observe during continuous casting. Therefore, we also did a numerical model. Well, Daniel, our student, also did a numerical model and this is just 1/4, so that's why it looks like this. So it's just 1/4 representation. We don't need to model the whole thing if it is symmetric. And then we're able to predict the liquid fraction as we go on time. So why did we use the bismuth tin alloy? First of all, for us to understand what type of cooling rates we observed. And it was very interesting to see that the center, as we do in continuous casting, will solidify much later, and that we will have a much faster cooling rate on the surfaces, and then it will slow down as we progress in time, giving us this kind of interesting curve, that we see. We call it S-shaped curve for initial cooling very fast. Then we have a period where it slows down, and then pretty much we have to the end a long solidification time. We saw this work. So this was our first test, what you saw. Then we decided to move into actual steel. And in the steel, then we were able to have a similar box made of, so you have the initial big box, sand in between, and then the mold, which will act as initial shell. For those familiar with continuous casting, this will act as our initial shell for solidification. Then we have the ladle, or what we saw as the ladle in our case in the video, and then a ton dish made of ceramic in between. We produce the melt of 70 kilos inside our vacuum induction furnace unit. And then we cast. These are the dimensions that you see here. And what was most interesting for us is to add true holes in this plate. And you can see them here. Through holes in this plate, we were able to create, to implement thermocouples, not only on the surface, but thermocouples actually inside the ingot as it solidified. So we were actually capable to track the temperature inside the ingot during the whole solidification process. Happily, since we had done this pretest, everything went well. And here you can see one of the structures, one of the ingots cut. This is a half cut from what is produced here. And we were so excited to see the classical structures that we observe during continuous casting, a columnar growth from the walls. And then, so now you're familiar with what is a columnar to equiax CET transition somewhere here. And then we have a equiax transition in the center. So we can have very defined structure that we are looking for. So what did we do this? So now we have a technique to replicate the growth that we observe in continuous casting. And now you can imagine all the variations that we can have. We can have less sand, we can have more sand, we can have thicker mold, thinner mold to achieve different cooling rates. And not only that, we also have a modeling technique. In this case, for example, Matthias and the Salish and Niels could do this in Turcast, model the heat transfer behavior, and then compare with the cooling rates that we are obtaining at the end. So this is, by the way, a cut at almost the bottom of the ingot. And then we will be able to obtain the plot of temperature over time, since we put thermocouples in the mold. And here you can see this, the center and on the surface. So we have the center was, I think, is T8, if I'm correct, somewhere there. It should be in this lower end. I recommend you, if you're interested, to pay a visit to Daniel Thesis, which is in the LTU repository for his masters, and then observe cooling rates going from 21. I think the fastest we observed was between 20 and 30 degrees per minute, and then all the way to very slow cooling rates. But what was encouraging is that we obtain very similar microstructures as we observe in the continuous cast products.